everyone. This video would focus on conic section, specifically on ellipse with center at 0, 0 or at the point of origin. And this is the 8th part. In this part, we're supposed to determine the standard equation of an ellipse and we're supposed to graph it. We are given the coordinates of the two vertices and the eccentricity. Before we go over this example right here, let's have a review on the parts of an ellipse and the two cases of an ellipse with center at 0, 0 or at the point of origin. We remember that there are two cases of an ellipse. The first case here is the horizontal ellipse. Before we go over this case, let's have the parts of every ellipse. The first part that we have here is the center. The center is halfway between the two diameters of the ellipse. The second part that we have here is the major axis. The major axis is the longer diameter of an ellipse that connects the two vertices passing through the center. So this means that both of these two dots that we have at the end of the major axis are the vertices. So one is the vertex and the other is the other vertex. The plural for that is vertices. So pretty much vertex is the end point of the major axis. Now we also have another diameter which we call as the minor axis. This is the shorter diameter of an ellipse that connects the two co-vertices of an ellipse passing through the center. So this point right here is a co-vertex of an ellipse, and this point down here is also a co-vertex of an ellipse. The next part of an ellipse is focus. So these 2 points right here are the focus of the ellipse. The plural for focus is foci. This focus is always gonna lie along the major axis. Please remember that foci of an ellipse are two fixed points on its major axis such that the sum of the distance of any point on the ellipse from those 2 points is constant. So those are the basic parts of an ellipse. Now we also remember that we have what we call as the semi-major axis. This is half of the major axis. So that means this runs from the center to the vertex, and we are going to represent this as A. On the other hand, we also have what we call as the semi-minor axis. This is half of the minor axis, meaning this connects the center to one of the co-vertices. And this line segment from the center to the co-vertex is represented as letter B. Now, on the other hand, from the center to the focus is represented as letter C. Now, using these letters A and B, we can derive the equation of a horizontal ellipse. Now, using these lengths A and B, we can come up with an equation of a horizontal ellipse, and that is x squared over a squared plus y squared over b squared is equal to 1. Now, notice that our A is the longer value, because this is actually half of the major axis, which is the longer diameter. Now notice that our A, which is the longer value, is the denominator of x squared. This means that if the denominator of x squared is bigger compared to that of the denominator of y squared, that means that we can come up with a horizontal ellipse. Now, we also remember that our A value, which is the semi-major axis, will always be greater than B, which is the semi-minor axis. That's always every time. And the equation that can be used to determine the length of C, that is from the center to the focus, is C squared equals A squared minus B squared. Now, let's look at the second case of an ellipse. For the second case of an ellipse, we pretty much have the same parts. The first part is the center. Again, this is halfway between the two diameters of an ellipse. We also have a major axis. This is the longer diameter of an ellipse that connects the two vertices passing through the center. Now, please notice that we call this as a vertical ellipse because the major axis is the vertical line segment. We also have the parts which we call as the vertex. There are two of them. We call them as the two vertices. These are the two endpoints of the major axis. We also have a minor axis that is the shorter diameter of an ellipse that passes through the center and that connects the two co-vertices. And again, along this minor axis, we have the co-vertices or the co-vertex if it's singular. These are the endpoints of the minor axis. Now we also have another part which we call as focus. So these 2 points right here are our foci. So pretty much these are the parts of an ellipse. So it doesn't really matter if it's a vertical ellipse or a horizontal ellipse. The parts would still be the same. Now we also remember that we have what we call as the semi-major axis. This is half of the major axis, which means this connects the center to the vertex. And we are going to label this as A. On the other hand, we also have what we call as the semi-minor axis. This is half of the minor axis, which means this connects the center to the co-vertex or one of the co-vertices. And we're going to label this as our B. Now, we also remember that the distance from the center to the focus is represented as letter C. Now, using these lengths A and B, we can therefore say that our equation for a vertical ellipse is x squared over b squared plus y squared over a squared is equal to 1. Now, notice that our a squared is under the y squared. This means that if the value under or if the denominator under the y squared is bigger than the denominator under the x squared, we are able to get a vertical ellipse. And we also remember that again, our A is always greater than B. Now to determine the length of C, we are going to use the equation C squared equals A squared minus B squared. So these are the parts of an ellipse, and these are the two cases of an ellipse. Now let's go back to the problem. Okay, before going further, let's have a review on the formula for eccentricity of an ellipse. By definition, eccentricity of an ellipse refers to how flat or round the shape of the ellipse is. Mathematically, eccentricity is the ratio of the distance from the center to the foci, which we usually represent that as letter C, and the distance from the center to the vertices, which we usually represent that as letter A. Now, we remember that if eccentricity is equal to 0, then the conic section is a circle. On the other hand, if the eccentricity is greater than 0 or less than 1, we are able to come up with an ellipse. We also remember that if the E value is closer to 0, then the ellipse tends to be more circular in shape. On the other hand, if the E value is closer to 1, then it is more oval or elongated. Now let's look at the eccentricity formula of an ellipse. You will see the two cases of an ellipse, the horizontal and the vertical ellipse. Now we remember that the distance from the center all the way to the focus is represented as letter C, and the distance from the center to the vertex is represented as letter A. On the other hand, if we get a vertical ellipse, it's pretty much the same thing. The distance from the focus to the center is represented as letter C, and the distance from the vertex to the center is represented as letter A. Again, mathematically, eccentricity is the ratio of the distance from the center to the foci, which is represented as letter C, and the distance from the center to the vertices, represented as letter A. We can therefore write the equation of eccentricity as E is equal to C over A. So this is the formula for the eccentricity of an ellipse. Eccentricity is equal to C over A. Okay, going back to the problem right here, where we are given the coordinates of the two vertices, and we're gonna plot this. So that's 0, 9. This is our first vertex, and the other one is 0, -9. That's the other vertex. From here, we can go ahead and say that the center of an ellipse is the midpoint between the two vertices, or the midpoint between the two co-vertices. Since we're given the two vertices right here, we can go ahead and use the midpoint formula to solve for the center between these 2 points, or the midpoint between these 2 points, or we can go ahead and count them, and we can go ahead and say that the center here is at 0, 0. So I'm gonna label this at 0, 0 right here. That's the center. And we also remember that this type of ellipse, since our vertices are located vertically from each other, we can go ahead and say that this is an example of a vertical ellipse. So I'm going to go ahead and write those information up here. Okay, since we already know that this is a vertical ellipse, I'm going to write the general formula of a vertical ellipse down here. Okay, notice that our a squared is placed under the y squared because this is again an example of a vertical ellipse. Now looking at this, we remember that the distance from the center to the vertex is represented as letter A. We can use the distance formula to determine the distance between these 2 points, or we can count it from here. That would be 1, 2, 3, 4, 5, 6, 7, 8, 9. So our A, because again A is the distance from the center to the vertex, is actually plus minus 9. And so other than that, we are also given an eccentricity of that's gonna be square root of 5 over 3. Now we can tell that we already have an a squared because we can go ahead and square this. Our a squared is actually 9 squared is 81. So we already have an 81 right here. So I can go ahead and rewrite this as, I left the b squared blank because we don't have a b here, but we're given the eccentricity. Now, we had a review on the formula for eccentricity. We remember that the formula for eccentricity is E equals C over A. We are given the E and we are given the A, so we're going to plug it in. Our A is square root of 5 over 3, so I put it in here. Square root of 5 over 3, that's the E. We don't know the C. And then we have an A, which is 9. So I'm going to put that down here. So we can go ahead and solve for C from here. So this becomes C is equal to, that would be cross multiply. So that becomes 9 square root of 5 over 3. So we can simplify this further. 9 divided by 3, that comes out 3. So this becomes a 1. This becomes a 3 here. So therefore, we can go ahead and say that our C is 3 square root of 5. So this is our value for C. Now, others are going to say, what is that C for? We needed a B squared. Now, we remember that A, B, and C are related in an equation. C squared equals A squared minus B squared. So that from here, we can go ahead and solve for B. So I'm going to show the work down here. So we can go ahead and plug the values in. We have our C here is 3 square root of 5. And then we square it. So that would be 3 square root of 5. And then we are going to square it. And that is equal to A squared, which is 81. So I write 81 right here minus B squared. So that from here, we can solve for B already. So that we can go ahead and simplify this further. We remember that we distribute these two to each of the parts right here. So squared of 3 is 9. So I'm going to write 9 right here. And then square root of 5 squared is just 5. So I write 5. And that is equal to 81 minus b squared. So I can add b squared from both sides so that we can solve it and make it positive. So plus b squared. And then that's going to be plus b squared also right here. So plus b squared. So this gives us... So b squared plus 45 equals 81. Now, others will say, where did you get the 45 from? So 9 times 5 is 45. So what I would do is subtract 45 from both sides. So this would be minus 45 minus 45 so that we are able to solve for b squared. So our b squared is 36. So we can go ahead and plug that in here. B squared is 36. This tells us that our b is actually plus minus 6. And this is where the co-vertex is going to sit. So that would be plus minus 6. So we go left 6 and we go right 6. So this is the point of the first co-vertex, and this is the other co-vertex right here. So 6 places from the center. And we can go ahead and sketch our focus or plot the focus on this graph that we have right here. Remember that this 3 square root of 5 can be rounded off or can be changed into its decimal version, and that would be approximately 6.71. So I go up and down 6.71. So that is 6.71 should be somewhere around here. So that's the first focus. The other focus would be 6.71. That should be the other focus right here. So I go ahead and sketch the graph and write the coordinate of the two co-vertices and the coordinate of the two foci that we have right here. So this is the equation of this problem that we have right here, and this is the graph of this equation. Now let's move on to the next example. At this time, I would encourage you to pause this video and try this problem out on your own, and when you're done, unpause it and check your answer. Okay, so we go over the problem here. We're supposed to determine the standard equation of an ellipse, and we're supposed to graph it given the coordinates of these two vertices and the eccentricity. So I'm going to plot these 2 points down here. Okay, now we remember that the center of every ellipse is the midpoint between either the two vertices or the two co-vertices. So we can determine the midpoint between these two coordinates or these 2 points right here, or we can use the midpoint formula to determine the midpoint between these two. But looking at this, we can go ahead and say that our center is located at 0, 0. So I'm gonna label this as the center right here. And we also remember that the ends of the two vertices would be the ends of the major axis. So we can say that our major axis is the horizontal axis. So this is an example of a horizontal ellipse. So I'm going to write that information up here. Since this is an example of a horizontal ellipse, I wrote a squared at the bottom of x squared because again, that's horizontal ellipse. And so we can go ahead and determine the values of a and b so that we can determine the standard equation of this ellipse. Now we remember that our a is actually the distance from the center to the vertex. So we need to use the distance formula to determine the distance between these 2 points, or we can count the distance between them. So that would be 1, 2, 3, 4, 5, 6, 7, 8. So that's a plus minus 8. And so this tells us that our a squared is 64. So I will plug the 64 into the a squared here. And so our equation will come out. Now notice that I left the b squared blank because we're not given the b squared. Instead, we are given the eccentricity, which is square root of 3 over 2. We will solve for b squared from this eccentricity. Now we remember that the formula for eccentricity is c over a. We are given the eccentricity, which is square root of 3 over 2. We are given the a, which is 8. We solve for c. I will show the work down here. So we have solved our value for c is 4 square root of 3. Now, how do we determine the value of b squared? Now, we remember that our b squared is related to the equation c squared equals a squared minus b squared. So I'm going to show the work down here. So we have solved our b squared, again, using the equation c squared equals a squared minus b squared, and that is equal to 16. So I can go ahead and write that down here for b squared, that is 16. And so this is the equation for this problem that we have up there. Now we remember that our b here is plus minus 4 because the square root of 16 is 4. Remember that the b is the distance from the center to the co-vertex. So I go up 4, down 4. So this is where the first co-vertex is going to sit. And then the other co-vertex will be down here. So I'm going to label that as co-vertex. So this is the 4 points that are important in order that we can draw the ellipse. Now we remember that the C is the distance from the center to the focus, and that distance is 4 squared of 3, which is approximately 6.93. So I'm going to plot that right here. So that is negative 6. So I go left and right 6.93 because the major axis is the horizontal axis. So this would be 6.93. So somewhere around here. So this is the first focus. And then this is the second focus right here, 6.93. So I label that as F. Now we can go ahead and sketch the graph of the ellipse and write the coordinates of both the co-vertices and the two foci. Did you get the same answers as this? Good. Perfect. If you find this video helpful, hit like and subscribe for more math videos. See ya!